Hi everyone, and welcome to the Tech Crux. In this session, we will discuss the concepts including the rule of total probability and Bayes' theorem. Beginning with the former one, it is a fundamental rule in probability theory that allows us to find the probability of an event by considering all the possible ways through which the event can occur. It is often used when the sample space is divided into exhaustive and mutually exclusive events. Let us understand this with an example. Meet Ryan. He decided to enjoy his day by going out to either hiking on a hill, visiting a museum, or going to a beach. Here, assume that these three events are collectively exhaustive, as there are only these three options available, and also mutually exclusive, as he can only do either one of them. Now we need to find the probability that Ryan will enjoy the day. So now we first assign the probabilities to each of these events. Let PH be probability of hiking on a hill, PM be the probability of visiting the museum, and PB the probability of going to a beach. And then we look at the probabilities of enjoying each of these events. Let us write them as P of E given H, that is the probability of enjoying when Ryan goes to hiking, P of E given M, which is the probability of enjoying when he visits the museum, and the probability of enjoying if he goes to the beach is P of E given B. So then the total probability of him enjoying the day will be given as the probability of going on hill and enjoying, or the probability of going to the museum and enjoying, or the probability of going to the beach and enjoying. Mathematically, this can further be written as probability of H multiplied by probability of E given H plus probability of M multiplied by probability of E given M plus probability of B multiplied by probability of E given B. And this is what we call the rule of total probability, where we are looking at probability of an event through all possible ways. So now this would be the total probability of Ryan enjoying the day. In case you are facing a difficulty of how we got this relation, revisit to our previous video where we discussed about the multiplication rule and the conditional probability. Let us consider one more example. In our previous videos, we took examples of burger, pastry, and ice cream. This time consider a case where we are interested in total probability of having an ice cream, and the only prior event possible is having a burger. In that case, we'll either have the burger, or we'll not have it and directly treat ourselves the ice cream. So, let's first assign the probabilities here. Say that PB is the probability of having the burger, and its complementary event be PB-, which is the probability of not having the burger. Also, we have the probability of having the ice cream given we already have the burger, and the probability of having the ice cream without having the burger. Then our total probability of having the ice cream will become probability of B multiplied by probability of I given B, plus probability of B dash multiplied by probability of I given B dash. Similarly, now say we have two options, either burger or pastry. In that case, the probability of having ice cream will be probability of B multiplied by the probability of I given B, plus the probability of P multiplied by probability of I given P. Similarly, we can find the total probability of an event given there are n exclusive and exhaustive events as the summation of I is equal to 1 to n, probability of AI multiplied by probability of event E given AI, where AI equals A1 A2 to AN. And these are collectively exhaustive and mutually exclusive events. In this way we can find the total probability of an event given there are n exhaustive and mutually exclusive events. Now based on our learning, let's discuss an example problem. The problem says that a group consists of equal number of male and female candidates, and of this group, 20% of male and 50% of female are unemployed. If a person is selected at random from this group, what is the probability that the selected candidate is employed? And the options share are 0.55, 0.6, 0.65, and 0.75. Let's look at the solution. Let E represent the event of selected candidate being employed, M represent the candidate to be male, and F represent the candidate to be female. The question also says that the group has equal number of male and female candidates. Therefore, the probability of selecting a male candidate will be equal to the probability of selecting a female candidate, and that will be equal to 0.5. Further, it says that of this group, 20% of males and 50% of the females are unemployed. So if we want to know the probability of the candidate being employed given he is a male, it will be 1 minus 0.2 since 20% of the males are unemployed, so this will be 0.8. Similarly, the probability of candidate being employed given she is a female will be 1 minus 0.5, since 50% of the females are unemployed, so this will be 0.5. Then the total probability of selecting a candidate who is employed will be calculated using the rule of total probability as the probability of candidate being male multiplied by probability of employed given male, plus probability of candidate being female multiplied by probability of being employed given female. And on solving, it will be 0.5 into 0.8 plus 0.5 into 0.5, which will be 0.65. So option C here is our correct answer. Now let us talk about a highly useful concept in probability, which is the Bayes theorem, which was named after an 18th century statistician, Thomas Bayes. It allows us to update the probabilities of an event based on new evidence or information. Let us take an example. Recently, a flu has been spreading in Ryan's neighborhood, which affects 1% of the people in the locality. Say that F is the event of flu, and the probability here given is 1%, or is equal to 0.01. So, Ryan decided to take a test and the test is 95% accurate in identifying the flu. If TP is the event of being tested positive during the test, we have given that probability of being tested positive given the flu is 95%, or 0.95. Now assuming the probability of being tested positive to be 5%. As per the Bayes rule, we can estimate the probability of having the flu given tested positive as the probability of being tested positive given the flu multiplied by probability of flu upon probability of being tested positive. And on substituting the values, we will have 0.95 into 0.01 upon 0.05, which on solving will be equal to 0.19, or 19%. So the probability of actually having the flu if tested positive will become 19%. Now let us understand how this formula came. Consider these two cases, where Ryan felt sick, probably due to flu, so he took the test. And second, where he took the test as a precautionary measure to see if he has flu. For the first case, probability of having flu and being tested positive can also be written as probability of being tested positive given the flu multiplied by probability of having the flu. While in the second case we can write it the probability of being tested positive and having the flu as probability of having the flu given tested positive multiplied by probability of being tested positive. Now if we look closely, these two terms should be the same. So on comparing these two relations, we can write probability of being tested positive given flu multiplied by probability of flu, which will equal the probability of having the flu being tested positive multiplied by probability of being tested positive. This can be written as the probability of actually having the flu if the test result is positive, which becomes probability of tested positive having flu multiplied by probability of flu upon probability of tested positive. And this is known as the Bayes theorem. Here, PF is called the prior probability before new information is collected, or in this case before the test is conducted. Probability of flu given tested positive is known as the posterior probability. This posterior probability refers to the updated probability based on the new information. That is, after the test results came. Probability of tested positive given flu is called likelihood, which refers to the probability of observing new evidence given the event has occurred. And the probability of being tested positive is called marginal likelihood, which is the probability of observing new evidence, regardless of whether the event has occurred or not. So as we see here, this method is particularly useful when we have an initial probability of occurrence of an event, and we want to adjust it based on some new information or evidence. It is a powerful method for analyzing and interpreting data in modern data analytics. Alright, now let's look at this relation more closely. Here probability of being tested positive can be given in two ways. One way is Ryan has the flu and tested positive, and another where he doesn't have the flu and still tested positive. Then we can update the above equation using the rule of total probability by substituting the denominator of this equation with probability of being tested positive having the flu into probability of having the flu plus probability of tested positive given not having the flu into probability of not having the flu. This is sometimes also known as the expanded Bayes theorem. Now similarly, if we extend it to n number of events where an event A corresponds to B1, B2, to be n exclusive and exhaustive events. Then using the Bayes rule, we can estimate the probability of occurrence of an if event Bi given A as probability of A given Bi multiplied by probability of Bi upon sum of probabilities of A given Bi multiplied by probability of Bi, where I equal 1 to n. Let us look at a related example problem. It says that a vendor received a lot of 100 electronic kettles. There is an equally likely probability that there are 0, 10, 20, or 30 defective kettles in the lot. If one of them is selected at random and found to be working, then what is the probability that no defective kettles are in the lot? And the following are the options available: 5 by 12, 3 by 16, 1 by 8, and 1 by 3. So, let's see the solution. Let G be the event of selecting the working or good kettle and Di be the event of I defective kettles present in the lot where I equals 0, 10, 20, and 30. Then we need to find the probability that there are 0 defective kettles in the lot given a good kettle is selected. Then, using the Bayes theorem, we can write it as probability of good kettle given D naught multiplied by probability of D naught, upon sum of probabilities of good kettle given I defective kettles, multiplied by probability of I defective kettles. Here, this denominator can be expanded like this. Now the question says that there is an equal probability of 0, 10, 20, or 30 defective kettles in the lot. And altogether they shall be equal to 1 upon 4. Now if we see probability of choosing working kettle from the lot of 0 defective kettles will be equal to 1. Since all the kettles are working here. Then, probability of selecting a good kettle when there are 10 defective kettles will be equal to 90 upon 100, since there will be 90 working kettles and 10 defective kettles. Similarly, probability of selecting a good kettle when there are 20 defective kettles will be 80 upon 100, and probability of selecting a good kettle when there are 30 defective kettles will be equal to 70 upon 100. Now if we substitute these values in our relation, so we get the following. Which on solving will be 100 upon 240 or 5 upon 12. So, A, here is the correct answer. And with this, we have learned in this video about the rule of total probability and the Bayes theorem and their applications. I hope you enjoyed this video and found it simple enough to understand the discussed concepts. Do consider subscribing, if not done yet, and please like, comment and share this video. We shall meet again in the next video. Thanks for watching. Bye.